morning, chemists. Let's get started. It was great to see everyone in lab yesterday, seeing you all in your lab coats and goggles, working as chemists. So actually the timing of the labs, along with our, accelerated fast-paced lecture, kind of works out perfectly. You guys did chapter 13, freezing point depression stuff yesterday. And tomorrow you will be doing BAR, which is bleaching of allure red. So you'll be looking at kinetics, specifically the second way that we determined a rate law, and that's using the integrated rate laws. Looking at, what are you doing? You're looking at the integrated rate law, so you are looking and graphing concentration changes with time. So the hard part is coming up with your Beer's law plot and actually measuring what the concentration of your dye is at certain times. Like, I don't know about you, but I can't just look at a red solution and be like, yeah, that's the concentration. No, we need an instrument to actually tell us exactly what is that concentration in molarity, and then you will take measurements at different time points. And what you'll see is, based upon how you graph that data, you will get different, hopefully one of those graphs will be a straight line, and you can make that conclusion on what the order of your reaction is with respect to the dye. I'll point out that the reaction that you're doing in lab and BAR, you're bleaching a dye. So there's two reactants, dye and bleach. But we are making it a little easier on you, and we are telling you that the concentration of bleach is so large, that it's in such large excess, that the concentration of that bleach does not change with time. So we're actually forcing bleach to be zero order because you're not really changing the concentration with time. So you're just focusing on, okay, what is the order of bleach? And you'll use the graphs to do that. So just how we set up the experiment, we can ignore bleach. Oh, so I meant the order of the dye. You'll figure out the order of the dye. All right, and so that was the second way we determined rate laws, is through the integrated rate law equations and graphing it. And now we are on this intermediate part where we're looking at specifics of activation energy and the Arrhenius equation. So we left off. We're right here. Oh, I forgot to make an announcement. If you have any, are searching for any faith-based accommodations for this 8-week course, so if you need accommodations for if you need to miss a midterm exam due to faith-based obligations, like a midterm, lab, or recitation, you need to contact the Gen Chem team by this Friday and give us those dates. So if you fall under this category, look at page 4 of the lecture syllabus where there's faith-based accommodations. It'll tell you exactly who you need to contact, what we need, but those have to be put in on Friday if you are looking for accommodations for those. Any questions about that? Okay, yeah, so it's due on Friday. Okay, yeah, so we left off talking about activation energy and the significance of that and how it's related to our little k, our rate constant, depending on, the energy needed to get over that activation energy changes the magnitude of k. If you have a big hill you have to climb, your k is small, your reaction is slow. If it's a small hill, you're more likely to get over, so those reactions are faster. So our Arrhenius equation, that's what this one is, tells us that the magnitude of k will increase if either activation energy is small, so your hill is short. Also, the equation says that. If you have a small negative number in this exponent, k will be bigger, or if your temperature goes up. And that kind of relates to our intuition, hot reactions go fast. If you heat it up, it goes faster. But the equation tells us that too. So this Arrhenius equation tells us our relationships between activation energy, rate constant, and temperature. This question is a little bit different, but before we approach that, I actually want to show the simulation here. I showed just like static pictures of these, but let's actually do and compare a chemical reaction where we inspect a single collision versus a multi-collision. and we think about, okay, in order for a reaction to occur, there has to be, the collision has to have enough energy to get over that activation energy hill. So let's look at this single collision and help me predict whether a reaction will occur or not. So this reaction, we have this yellow ball and then we have a molecule. So if we smash them together, hopefully we break a bond and we form a bond. So let's see if that happens. So I have this like plunger where I can like kind of like ricochet that yellow ball. And so you can see I'm changing the energy of that collision and we can see it. So let's see if I let go right here, if I let go, will a reaction occur? Why? Doesn't get over the hill. So let's see. Do you see it moving? Yes. Do you see any bonds being broken or made? No. So did a reaction occur? No. All right, so let's try again. Reset. So where should I put the energy marker? Over the hill. Yeah, so if I let go right there, will a reaction occur? All right, so let's see. Do you see the atoms? They're actually, there's a bond every time there's a collision. A bond is broken and a bond is made. So a chemical reaction is in fact occurring here when that single collision, collision energy is above that activation energy, or above that crest. Oh, okay, yeah, so there we go. All right, so let's look at many collisions. All right, that was just a single collision. The line that you see was just the absolute energy of that single collision when I, pulled the plunger. So let's look at the many collision scenario. This one's a little bit harder to see. So now I have a bunch of those yellow balls and a bunch of those molecules present. So what I want you to look at is that this middle bar graph. All right. So there's 4 different species, and that bar graph is telling you how much of each are there. So right now you see 2 bars occupying all of the reactants. So right now our container just has a ton of reactants in it. All right, so if a reaction occurs, we should see the bars move and you start to make products if a reaction occurs. All right, so same idea here. I'm gonna change the energy of the collisions, but through temperature. So I can either heat or cool this container, and I can change the language here. I can change the average kinetic energy of the sample. So let me play this. So let's do the easy one first. If I put that green line, that average kinetic energy way above the crest, will a reaction occur? Yes, yeah, so let's do that. So let's heat up this baby. Heat. Go, 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 go. There we go. All right. Yes, I made it over the crest. Is a reaction occurring? Look at the bar graphs. Yes, yeah, you see, okay, yeah, you're consuming some of your reactants and then you're making some products. So a reaction is occurring because our average kinetic energy is above the threshold. All right, but this one's a little bit different. I'm gonna reset this. Oh, whoops. Okay, so I need to put a bunch of A in there. I'm gonna put a bunch of B in there. So I'm gonna do the same thing as I did before. Show bar graph. Okay, but this time I'm not gonna crest it. I'll just kind of heat it up a little bit. So if I put it, oh crap, the reaction's already happening. Yes. So the idea here is if I just leave the bar, our average kinetic energy under the crest now in this many collision system, do we make products still? Yes, we do. But that's so weird. In our single collision example, if we were below that crest, we didn't make any products, but now we do. What's the difference between, in this example? There's more stuff. Yeah, there's more collisions happening, and not all of them have the energy of that green line. That's just average kinetic energy. Some of those collisions are going to be slightly higher in energy. Some will be lower because of our Maxwell-Boltzmann distribution. So we see that we do, in fact, still make some product, even if we're slightly below that threshold, because there's just a chance that one of those collisions will have enough energy to overcome that activation energy barrier. Right? So that's the difference between single collision and multiple collisions. All right, so let's exit that so it doesn't eat my RAM. So let's go back to the question now. So we see the rate at which reactions occur depend on how big that hill is, and the temperature, because that tells us average kinetic energy. So I asked you for this specific question, I give you two temperatures, and I kind of give you two rate constants in a way. And I asked you, okay, we talked about a lot of different equations that talk about rate constant, temperature. Which equation do we use? We use this third equation, because this is the equation that compares two temperatures to two rate constants. We could use this equation, but we would have to do like a system of equations, and it would be a lot harder. Just use the equation that already has two temperatures, two rate constants. So we just need to do a little bit of reading comprehension here. All right, I tell you that the rate doubles when the temperature increases from 20 degrees Celsius to 60 degrees Celsius. So is that my T1 and T2? So do I put 20 and 60 in here? 20 and 60? Yeah, so add 273, because with this R, the gas law constant, it's in Kelvin, all right? So we want to convert those values into Kelvin first. So T1 is equal to, what is that, 298 Kelvin? So that's your 20 degrees Celsius. T2, which is the 60 degrees Celsius, is something like 333 Kelvin. All right, so those are my two temperatures. So now this is kind of the hard part. What is K rate constant 1 and 2 there? I don't actually give you numbers, but here's the thing. If you look in this equation, see how it's a ratio? So for funsies, if I just tell you the rate constant at 298 is 1, based upon your reading comprehension, what must the rate constant of the second temperature be? 2, yeah, because I said, oh yeah, your rate constant doubles, so just make up a number. All right, it doesn't matter because we're putting it as a ratio inside the equation. So if we look at, what is known and what is unknown, all right, we know our K's, we know our T's, R is a constant, and so you can clearly see, oh, we just solved for activation energy here. All right, and so this does require a little bit of, more complex math than we've seen so far. So natural log, and be really, really cognizant of, are you putting in K1, T1, K2, T2? So just be careful here. So in our equation, we have natural log of K1 over K2. So it's 1 over 2 equals activation energy, that's what we're solving for, over R, so 8.314 joule mole Kelvin. So you can see that when we solve for activation energy, it will have the unit of joules per mole. And then now we do the inverse temperatures. So just be very careful here. It's T2, inverse T2 minus inverse T1. So it's 333 to the negative 1 minus 298 to the negative 1. So do make sure you get those in the right spot. All right. You are given this equation at the exam, or for the exam. So yeah, we just solve for this. So let's do that. So natural log of a half. So we have negative 0.693 equals, okay, 333 to the negative 1 minus 298 to the negative 1 equals EA over 8.314. All of that in the parentheses is negative 3.527 times 10 to the negative 4. All right, and so just move things around. So 0.693 times 8.314 divided by that number we just got. So we get that activation energy. Oh, wait. Did I do this right? Oh, 298. No, sorry. This isn't 298. This is 293. No one corrected me. Were you thinking that in your head? Yeah, so this is 293 because it's that's what I get for doing it in my head. 20 degrees plus 273 is 293, not 298. My answer was a little bit off than my key. So this is to the 293 to the negative 1. Okay, now let me redo this. 333 to the negative 1 minus 293 to the negative 1. Okay, so this is 4.099 to the negative 4. All right, so let's do this again. 0.9 or 693 times 8.314 divided by that 4.099 e to the negative 4. All right, there we go. So I get an activation energy is 14056. And so based upon this unit of R, that tells us what the unit of activation energy is. It's not a kilojoule, it's actually a joule. This is a joule per mole. But this question is asking what is the activation in kilojoules per mole, so just take one step further, divide by 1,000 to get this reaction has, its activation energy is 14.1 kilojoule per mole. So that value, that energy value is related to, let's go back here, it would be equal to whatever this energy is. All right, so this, if this was the reaction, we could measure that energy requirement is 14.1 kilojoules per mole. So that's how big your hill is. And that's what we just calculated. We are able to get that if we know the rate constant at 2 different temperatures, using the 2-point form of the Arrhenius equation. All right, so that's a little bit more math. There's more places to go wrong. I already made a mistake. To know activation energy. So there's a lot of ways I can ask questions like this. I could instead give you the activation energy of a reaction. I could give you a rate constant and a temperature, and at a certain temperature, and I can ask you to estimate how fast a reaction will go at a different temperature. And so you can get that if you know the activation energy. So the ideas are here that, you know, looking at this equation, I can give you any set of these variables and you just solve for that remaining piece. Understanding these K's related to rate constant, those are your 2 temperatures, how fast your reaction goes at those 2 temperatures, all related to activation energy, which is a constant for that specific reaction. All right, so there. Putting together the idea of collisions and kind of on the molecular particle scale why reactions are sensitive to activation energy and temperature. All right, so we're done with that section. Now we're going to move on to the very last section, and this is the 3rd way we get a rate law. So let's review the ways we got rate laws. Okay, the first way was method of initial rates, where I said if I double the concentration of something, but I see a 4-fold increase in rate, what's the order of that reactant? 2. Yeah. If I triple the concentration of a reactant, but I see no change in rate, in our overall rate of our reaction, what's the order? 0. Yeah. So that's the first one, method of initial rates. The second method we did was graphing, so the integrated rate laws. So this last method is a little bit more theoretical, a little bit more conceptual, and I think it's fun. There's very little math here. So the idea here is, you know, I can have a reaction that's like A goes to B gives us C, right? But a reaction, if I give you an overall reaction, it doesn't necessarily mean A and B collide with one another and you get C. Not necessarily, if that's your overall reaction. We actually want to think about the individual steps it takes to get to a final product. So like an analogy I like to use is like building a bike. If you think about all the specific little steps required to build a bike, that's kind of like a reaction mechanism, right? Like you can't just build a bike in one step. I don't know about you, right? Like you can't just build it in one step. You have to, you know, build the tire, put on the pedals, put on the handlebars, like all of those little steps add up to the final product of, okay, you make some bikes. And so far we've kind of just looked at, okay, what is the rate of products being formed? So now we're going to inspect what are the little steps required to actually go from product or reactants to products. So that's what we're going to inspect here. That reactions actually take a step-by-step pathway to get to its final destination. All right, so reaction mechanisms. Not all steps happen in one step. You don't just, you know, throw together your reactants to make your product. We want to think about these step-by-step molecular pathways. Sometimes, you know, more than one step happens here. So let's just look at this reaction coordinate and think about, don't look at the answer over there. How many steps does it take to get to your product? You go over one hill and then you go over another hill. So this is a 2-step process based upon this reaction coordinate diagram. You go over one hill and then a second hill. That's 2 steps. So what I have over here on the side is I'm just telling you, oh, these are the specific elementary reactions that make up this reaction pathway. Here's your first step, there is your second step, all right? So 2 steps are happening. And so kind of like Hess's law, we can add up those 2 steps to give us our overall reaction. And this is what we observe in lab. So if we kind of treat this like Hess's law, A plus B is giving us AB. But then in the second step, AB is combining with another B to give us our product BAB. So are there any species we can cancel to get our overall reaction? If just treat it like Hess's law. AB gets made and then consumed. So you see that AB is made, but then consumed, and it doesn't show up in the overall reaction, but it is in fact made. And so in this case, AB is an intermediate. All right, because we canceled it out. It's made and then consumed in your reaction. And so you see how these things add up. So there's 1A in our reaction, all right? Oops. There's 1A in our reaction, and then there's 2 B's, and you see that in the balanced overall reaction, and then our product here is BAB, all right? So our 2 steps add up to our overall reaction. So the big point in this part of the chapter is you're not expected to come up with a mechanism on your own. You'll never be asked to do that, ever. Usually how we assess this, this part of the chapter is I give you a mechanism, and you need to determine what the rate law is, right? So you don't have to come up with a mechanism by scratch. And so the idea here is these mechanisms are just a proposal. All right, we can't actually see atoms. We can't see them being made or broken. The simulation that we did, it was just a simulation. It's what we think will happen. And so what we are the big idea in this part of the chapter is, can you interpret a mechanism and see, does it match our experimental data? That's what your job is, not to make up a mechanism on the spot, all right? So let's go through the steps of how to figure out a rate law from a mechanism. So remember all those times I said your rate law is not related to stoichiometry? All the times I said that. You have to look at the experimental data. Yeah, like if it's like 1A plus 2 B's gives C, you can't just say that A is first order, B is second order. I said that for the first two methods. Now, finally, we can say that. So when I give you a mechanism, these mechanisms are composed of very simple elementary steps where one collision is happening. So when we have a elementary step, we can just use the stoichiometry to get the orders of the reactants in the rate law. All right, so you can finally do that, but only for elementary reactions. So here's an example. If I give you a step in a reaction mechanism, the rate law for that step is just equal to whatever the concentration of the reactants are. So in this step where it's unimolecular, there's only one reactant, the rate law is simply A to the first order. If you have a elementary step in your mechanism where 2 A's are combining and colliding, right? There's 2 A's. Then you have a second order reaction with respect to A. If you have A and B combining, your rate law for that step is A times B. So finally, when we're only working with elementary reactions, so single steps in a mechanism, you can actually just take the concentration, the stoichiometry of the reactants, and that becomes your rate law for that step. This is the only time you're allowed to do it, right? Okay, so we have unimolecular, bimolecular. There's also tri or termolecular, where 3 particles come together in an elementary step. So if we're just following the trends here, that first termolecular one would be third order with respect to A. But termolecular elementary steps are not very common because when we think about a collision, a simple collision, usually it's just 2 things coming together and colliding. It's very statistically unlikely 3 things collide with one another in the same space at the same time. That's very unlikely. So Most commonly, you're going to see uni and bimolecular elementary steps. Okay, so let's do this. Let's actually practice it. Okay, so here, I told you, I'm never going to make you make a mechanism, come up with a mechanism. So here is a mechanism I'm giving you. I want you to interpret it. So here's step 1 and step 2. So let's get the overall reaction first. So let's look at these 2 steps. H2 combining with ICl gives us these things. HI combines with ICl to give us those things. Is there anything that can cancel? HI, yeah. And then everything else is good, right? Yeah. So it looks like this reaction is H2 plus 2 ICl gives us I2 and then 2 HCl. Do you agree? Yes. Okay. And you can check for yourself, you know, are the atoms balanced on each side? It looks like I have 2 hydrogens. Yep. 2 chlorines. Yep. 2 iodines. Yep. So it's all balanced. Good. All right. So again, when you get the overall reaction, you just take the steps, add them up, treat it like Hess's law. All right, so let me delete the, so then what is HI? Since it's made, but not in the overall equation, it's an intermediate, yes. I think that's the last, yeah. Identify the intermediate, so HI is an intermediate, okay, great. So now let's look at the individual steps and determine the molecularity of each. So I'm just asking you how many how many particles are colliding in each step. So both steps, so step 1 is what kind of molecularity? Bi, yeah, because 2 things are colliding. What about the second one? Also bi, because 2 things are colliding. Great. All right, so let's get the rate laws for both of them. All right, so the rate law for the first step, all we have to do is say the rate for this first step. I'll just write it up here. I'll write it next to the equation, all right? Rate of the first step is equal to the rate constant for that step. I don't know what it is, but it doesn't matter, all right? Times the concentration of both those reactants. So H2 times ICl. That's it. That's the rate law for the first equation, or the first step. You just take the reactants. And so the rate law for the second step is equal to a different K. It's a different rate constant, but still times the concentration of reactants. So HI times ICl. That's it. All right. So those are our rate laws. So I like saving mechanisms for last because I think it's the easiest. All right. So you're finally allowed to just take the stoichiometry and turn those into your rate laws. All right, so we're not quite there yet. We haven't gotten an overall rate law for this reaction. We just have rate laws for the individual steps. So this next portion tells us how we actually get the rate law for an overall reaction. And the big idea is when there's more than one step involved in a reaction, there's multiple elementary steps, whatever step is the slowest determines your overall reaction rate. The slow step determines your overall reaction rate. I have it in a box because I think it's important. So when you go to bed tonight, say that 10 times to yourself. The slow step determines your overall reaction rate. So in this class, we'll study 2 different kinds. One where the first step is the slow step, and then the other one, which is a little harder, is when the second step is the slow step. So think about like making a bike. Pretend that you and a friend, you're building a bike, and your job is to build the bike, and your friend's job is to slap a bow on the bike, and then it's done. Which step do you think is the slow step? Building the bike or slapping a bow on it? Building the bike. So if your boss is watching you and looking at the output of bikes being produced, which step is going to determine that overall output? Is it slapping a bow on it? No, it's the building the bike part. It's the slow step determines what output you see, all right? So yeah, So the idea here is, you know, this is building a bike. There's your first step. It's really hard to do. It's slow. But then slapping a bow on it is just kind of this like little hump at the end that happens very, very quickly. So again, the output of products that you see are dependent on this first slow step. All right. So in this mechanism, I'm telling you that the slow step is the first step. So what is the overall rate law for this entire reaction? Do we care about the second step? No, we don't. So the rate law for this reaction is just dependent on that first step. That first step is an elementary reaction. So all we have to do is say that rate equals K, the rate constant for that first slow step, times the concentration of A times the concentration of B. That is what the rate law is for this reaction, because it's the slow step determines the overall reaction rate law. Right? Second step doesn't matter. Second step doesn't matter. All right? And so A and B combine to make AB, which is an intermediate. But the thing is that intermediate is consumed basically right away because it's in the fast step. So that's why you don't see that contribution in the overall rate law. So this example would be, you know, the first kind of mechanism, slow first step. That's the easy one. You just take the reactants from that first step. Right, we're going to do another one? Yes. Okay. So here's your overall reaction. Here's a proposed mechanism. You can cancel things to prove to yourself that these two steps add up to the overall mechanism. All right. So which step is the rate limiting step? Which one do we care about here? The first step. Yeah, because it's the slow step. All right. So what's that rate law for that step? It's going to be rate. So this is for the slow step. Rate equals K times what? NO2, but it's squared. Yep, squared. So what's the rate law for the overall reaction? We got the rate law for the slow step, so what's the rate law for the overall reaction? It's the same thing, yes. So we can just nicely done, we can just copy and paste. Okay, we can just copy and paste. All right, so that's the rate law for the entire reaction. So it looks like for this reaction, it's second order with respect to NO2. And then what's the order of CO? 0. Okay, so according to the rate law, if we doubled the initial concentration of CO in this reaction, would we change the rate law? Or sorry, overall rate? No, we wouldn't. But what if we doubled the initial concentration of NO2? Would we see a rate change? Yes, we would see it increase by fourfold. Yeah. So it's still all these rate laws, they're still related to what we talked about previously. All right, great. All right. Okay, so let's do another one. Decomposition of hydrogen peroxide. What's the overall chemical equation? So again, treat it like Hess's law, see what we can remove here. So what cancels? What can cancel from these reactions? IO minus, yep, that cancels. And what else? If something else can cancel? I minus can also cancel, yep. So then we add those two things up. So we see two H2O2s, that's peroxide, gives us 2 waters, and 1 oxygen. And we see that it is balanced. So IO minus is what kind of species, since it doesn't show up in our, it's an intermediate. But what is I minus? It is a catalyst, yeah. And what makes it different? Both of these, they get canceled out. They're not in the overall equation. But in an intermediate, right, IO minus is made and then consumed in the next step. But I minus is a little bit different. Track where I minus is coming from. You add it, all right, it's consumed, but then it's made at the very end. So see how there's a small, subtle difference there? So I minus in this example is actually a catalyst, not an intermediate. Even though it's canceled out, it's just its placement is a little bit different. It is consumed and then made at the end. So it's a catalyst. All right, so Without doing much work, what is the rate law for this process? A, B, C, or D? A. Why is it A? Why is it A? The slow step always determines your rate law. Slow step always determines your rate law. Right? Okay. So for this reaction, which graph would be consistent with this mechanism? The first one, second one, or the third one? Can it be the first one? No, what's wrong with that? That one's one step. Yeah, but I just gave you the mechanism. It's 2 steps. So which graph is it? It's the second one. Yes, the middle one, right? Because the middle one, the first step has the biggest hill. The second step has a small hill. So that is related to a slow first step, fast second step. So it's not this one because the third one, because that would equate to a fast first step, slow second step. All right. Okay, so that's what this one would look like. All right, so one last thing for this question. So this is the same reaction, the decomposition of peroxide. Where on this reaction coordinate diagram, so A, B, C, D, or E, is the concentration of IO minus the largest? Think about what IO minus is. Is it a reactant? Is it a product? Nope, it's a intermediate. So if you are on this graph, where will that species have the largest concentration? At spot C, yes, C, because it's an intermediate. If the species we cared about was a reactant, then it would be A. If the species we were looking at was a product, then we would say E. All right. Can you isolate anything that is in spots B or D? No, those are activated complexes. They're transition states. They're not actually stable compounds that you can like put in a bottle, like extract from your reaction and like keep in a bottle. That it's not stable there. But you can see, remember my ball analogy that I mentioned? Would a ball be very stable? Yeah, it'd be able to live at spot C. Yeah. Okay, great. Yeah, so the answer is C. All right. Okay, this is the last way I can kind of ask a question. All right, for this reaction, 2A plus a B gives us CD. So that's the overall reaction. That's not an elementary step. I'm telling you that the rate law is rate equals K times the concentration of B. Which mechanism is consistent with this rate law? The first one or the second one? So I'm doing it backwards, right? I'm telling you, here's the rate law, which mechanism is consistent with it. So kind of an easy way to do it is just get the rate laws for both of those mechanisms and see which one matches. So let's just do that. What is the rate law for that first reaction? Rate equals K times A and B. Great, does that match? No, so this cannot be the mechanism. It can't be the mechanism. It doesn't, it's not consistent there. But what about the second one? Rate equals K times what? B. Do we care about any of the other steps? Nope, just the slow step. So we see that it's that second mechanism is consistent with, you know, what we observe. So that's another way I can ask it. A little bit harder, I guess, right? Okay. All right, so those are the easy ones. Those are the first steps, the slow step, just ignore everything else. So now let's do the second type of mechanism here. Fast first step, slow second step, right? But you know, our the way we approach this is still the same. You know, the mantra that I want you to go to bed tonight and say is the slow step is your rate determining step. Your slow step determines the overall rate of the reaction. So that still holds true here. But let's see what happens with this mechanism. All right, 2 steps. Fast first step, slow second step. Slow step always determines the overall reaction rate. So let's get that rate law for the second step, because the second step's slow this time. So rate for that slow step is equal to K, and I'm just going to put a 2 there to indicate that it's the rate constant for the second reaction. And then what do I multiply by? B and M. That's it. Am I done? I'm actually not done because we have a problem. M is in our rate law, but is M in the overall reaction? No, M is actually an intermediate. We can't have intermediates in our overall rate law. All right, so we're going to do a trick to get rid of it. We're actually going to use the fast first step to help us get rid of it. So I'll show you how we do that. So we're not allowed to have M in there. So let's get rid of it. So this is the trick to get rid of that M intermediate. We're using the rate of the fast first step. So the idea here for this trick is we're saying that the fast step is an equilibrium, where the rate of the forward reaction is equal to the rate law of the reverse reaction. All right, that's equilibrium. We're going to talk about that in chapter 15, so just have some blind faith in me right now. So step one is an intermediate, is an elementary step. So tell me what the forward rate law, the rate law for the forward reaction for that first fast step. Tell me what it is. It's K1 times the concentration of A, but it needs to be squared. Great. Now, tell me the rate law for the reverse reaction. So in the reverse reaction, the products are now your reactants. So the reverse rate law is not going to be K1, but K negative 1. I'm trying to tell you it's the reverse reaction. All right, so then multiplied by what? M. Great. Do you see where we're going? Now we have an equation where we can substitute what M is. So just move some junk around. You'll get that the concentration of M is equal to K1 over K negative 1 times A squared. All right. So basically what I did, as I said, set equal the forward rate law to the reverse rate law of the fast step. Rearrange some things to isolate the intermediate, and now I'm going to get rid of the intermediate in my original equation. All right, so do you see how all that works? Okay, so yay, I can get rid of M now. So let's plug that in. So we get the rate of the overall reaction is equal to K1 times K2 over K negative 1 B times A squared. All right. So that's the full rate law. And so we can simplify this as well, because notice how I have a lot of K's in there. But the thing is, when you actually observe this reaction, all those K's are combined. So this can easily just be rewritten as K, just K overall, like an overall K, times B times A squared, right? So basically all of those K's just combine into one K. Right, but I wanted to show, hey, each of those individual steps have their own case. But I think there's some mastering chemistry homework problems where you'll do this, but they just ask you report just one K, an overall K. Right, but what's important here is now we have the orders of our overall rate law. So A is a first order and B is second order. And I would say this is a harder type of question, where the second step is the slow step. What? What part? Okay, well, we already did the easy one, where the first step's the slow step. Now, this is as hard as it gets. The second step is the slow step, but it's still the same rules apply. The slow step determines the overall rate law. We just have to do a little bit of manipulation to get rid of that intermediate. All right? Okay, feel good? Let's do some more practice. Okay, all right. Let's get the overall balanced equations for all of these mechanisms. All right, so let's do this first one. What cancels? M. Anything else? No, that's it. So A plus B gives C and D. M is what? An intermediate. Okay, great. Let's do the next one. What cancels? M, yeah. Is it, what is it? Yeah, it's 2A, sorry. Thanks. Okay, the second one. What cancels? M again. And what's the balanced overall reaction? 2A plus B gives us C and D. Is that interesting? Yeah, those two reactions, they, different mechanisms, but same overall reaction. Interesting. All right, let's do the next one. What cancels? And N. And then what's the overall balanced equation? 2A plus B gives us C and D. And what do you think the last one is? The same thing. Yeah, I think so, hopefully. M cancels, N cancels. Yeah, so 2A plus B gives C and D. Yeah, so these are 4 examples of different mechanisms, but they all yield the same overall reaction, where you throw in 2 equivalents of A, an equivalence of B, and you pop out a C and a D, but different mechanisms. Do they all have the same rate law? No, because the mechanisms are different. So what do you think the next slide is? We're going to determine what the rate law is for all of these proposed mechanisms. All right, so let's get the rate law. So let's just work in the same order. All right, what kind of mechanism is this? Slow first step. So is it hard? No. So what's the rate? The rate law. Rate equals K times A times B. Do you have to do anything else? Nope, that's it. So all this is saying is that this reaction is first order with respect to A, first order with respect to B. Okay, so the next one. Is this one a little harder? Yeah, it's a little harder. So again, slow step determines the rate law. So rate equals K2 times B times M. Am I done? Nope, what's wrong? Can't have M, so how can I get rid of M? Use the fast step. So the fast step is the rate of the forward reaction. So K1 times A squared equals K negative 1 times M. So that right-hand side, that is the reverse reaction. So going in the reverse direction. M is the reactant there. So just move things around. Oh, we actually already did this one, but we'll just do it anyway. So M is equal to K1 over K negative 1 A squared. And so we can plug that into our original rate law for that slow step to get rid of M. So we see the overall rate is, I'm just going to call all of it K times B times A squared. So that's the overall rate law for that one, for the slow second step. All right, so let's do another one. This one. Is this one easy or hard? Easy, yeah. So rate equals what? KB. Do we care about the other steps? Nope. All right. What about this one? A little harder, yeah, but still the same idea applies here. The rate of your overall reaction is always determined by the slow step. So we care about the second step. So the rate law for that slow step is K2 times M times A. Can I be done? No. Got to get rid of that M. So what am I going to do? Use the fast step. But which one? The one before it, yeah, because that's the one that has M in it. So I'm going to say for the fast step that K1, so the rate constant for the forward reaction, times B equals the rate constant for the reverse reaction times M. All right, so we see that M concentration is actually analogous to B concentration. So if I insert that into the M variable back into my rate law, I get the rate of the overall reaction. So K overall, rate constant overall, is equal to B concentration times A concentration. Do you agree? Yep. All right. So those are the different kinds of rate laws I can give you. Is it that bad? Is this one fun? I think it's kind of fun. Yeah. All right, So we just went through all the different ways we can get a rate law. This is how I elevate a question for an exam. It's by combining different methods. Okay. But before I do that, so it's just some terminology here. I can never actually say that a mechanism is correct. I will never ask you, is a mechanism correct? Because we can't actually see atoms. All right, so these mechanisms are just proposals. It's just what I think happens. So oftentimes on exams, I'm going to ask you, is the mechanism consistent with experimental data? We can say if experimental data is consistent with what the mechanism is. We can't say that the mechanism is correct. That is just kind of it's a, science terms, right? That we can't say for sure that something is right because we can't actually see it. We can just say that it's consistent with the observations we see. So that's a small detail, all right? So let's do that. Okay, so here's your overall reaction. You can prove it, that the two steps add up to the overall reaction. And there's the mechanism. What am I asking? And so here, I'm elevating this question by adding a different rate law method. This table is what kind of method? The first one we studied, the method of initial rates. And I'm asking you, is the mechanism consistent with the data? So the strategy here is get the rate law from the mechanism, get the rate law from the data, and see if they match. So let's do that. So this mechanism, is it hard? Nah, not really. So the rate law for this mechanism, slow first step. So we're just going to say the rate is rate constant times NO concentration, or NO2 concentration, times F2 concentration. That's it. That's it. Yeah? Okay. So there's the rate law for that first reaction. So let's look at the experimental data and see, is this rate law consistent with that experimental data? Okay. So what's the strategy here? We want to see how one reactant changes and how it affects the overall rate of the reaction. So if I want to figure out the order of F2, what trials do I want to look at? 1 and 2. What's special about experiments 1 and 2? This one stays constant. Yeah, so since that stays constant, it's not affecting the overall rate. So I see, oh, F2 triples. How does the rate triple? Or sorry, how does it change? It also triples, yeah. So what does that tell us about the order of F2? It's first order. Okay, great. So we got the order of F2. What experiments do we want to use to get the order of NO2? 1 and 3, yeah. 1 and 3, because now F2 stays constant. It's not affecting the overall rate law. So I see that NO2 is changing. It is doubling. How does the initial rate change? Double. So what is the order of NO2? First, NO2. Cool. First order. Okay. So if this was a method of initial rates question, you would get that the rate law of this experimental data shows that the rate law is rate times K times NO2 to the first power, F2 to the first power. Okay, now let's answer the question. What does that prove? This experiment proves that the mechanism is correct? No, we're not allowed to say that. So what's the answer here? It is C. The experimental data is consistent with the proposed mechanism, right? Because the rate laws, the resulting rate laws we got, they match one another. They're both first order, right? That's how I elevate a question. You do the mechanism, you see how it fits with experimental data. So let's do another one. Same idea. Does the data match the mechanism? So first, so I give you what I think the rate law is. So here's your overall reaction. Here's the proposed mechanism. So NO2, so it's again slow first step, so fairly easy there. Okay, so do you agree that this is the rate law with that mechanism? Yep, okay, cool. So first order with each. So yes, I agree with this. So here's the experimental data. Does that data agree with the proposed mechanism? No? Why? What does this first graph imply? That NO2 is first order. But I want that. That's good, right? But what's wrong with the second graph? F2 is second order, and how did you know that? How it's graphed as a straight line says, since we graphed it 1 over concentration, this implies that F2 is second order, right? So this experimental data is actually saying that the rate law is rate equals K times NO2 times F2, but it's squared. So these are not consistent with one another, right? And again, that's how I elevate a question. But was it that bad? No, it wasn't that bad. Okay. Again, I think mechanisms are fun. Okay. Okay, here's another one. Proposed mechanism, slow, fast. There's the overall reaction. Is this reaction coordinate diagram consistent with the mechanism? Yes, what detail makes it yes? Yes, the beginning, the first step has the largest activation energy. Okay, so it's going to be the slow step. Yep, so yes, it is. Perfect. All right. Is there more? Okay, nope, that's it. All right, those are mechanisms. Which method do we like the most? Initial rates, graphing with the integrated rate laws, or mechanisms? Mechanisms are fun. They're like a little puzzle, all right? But again, how I elevate it on exams, because it is rather straightforward, as long as you understand that a mechanism is proposed of elementary steps. It's only for elementary steps where we are allowed to just take the stoichiometry. That becomes our rate law. That's the only time. But yeah, how I elevate it is I relate it to either graphing or method of initial rates. Okay. All right, so we'll move on to the last part of the chapter. I'll just go through this really quickly, and it's the idea of catalysts, that we can add a kind of like a reactant to a chemical reaction and make that reaction go faster. So I just want to talk briefly about the factors that make a reaction go faster. Let's talk about the ways we can make a reaction go faster. We've already talked about that. Heat it by increasing temperature, or what's the other way? Lowering the activation energy. So that is what a catalyst does. A catalyst makes a reaction go faster, so increase K, your rate constant, by lowering the activation barrier, that it's making the hill easier to climb. And there's a couple factors that do it. Yeah, catalysts operate by lowering overall activation energy. All right, so what we'll see is that the factors how a catalyst work is essentially it's changing your activation energy. That's how you increase K. Or some catalysts also increase your collision factor, your frequency factor. It allows more efficient collisions. So those are the two ways that a catalyst works. And so how we determine what a catalyst is in a mechanism is it's usually consumed and then produced by the end of the reaction. And that's different from an intermediate. An intermediate is produced and then consumed before the end of the reaction. So small little difference. And I'll point out that enzymes in our bodies are also catalysts. Enzymes, you can think about like the lock and key model or the induced fit model, where enzymes in our body bring together proteins or whatever substrates to facilitate chemical reactions forward, typically chemical reactions that aren't very energetically favorable. So yeah, enzymes in our bodies are just biological catalysts. They operate on the same principle, either lowering the activation energy of a reaction or improving the collisions. All right, so let's look at an example. So we kind of looked at this before, the decomposition of hydrogen peroxide. You ever buy that at the store? Hydrogen peroxide, yeah, it comes in that like brown bottle. Yeah, so here's how peroxide decomposes. It's a solution and it produces O2. O2 gas, right? So you're making a gas. So when peroxide decomposes, it produces a gas. So let me ask you, when this bottle is in your medicine cabinet, does the reaction go forward? How do we know? How do we know that the reaction doesn't go forward in your medicine cabinet? It would explode, yeah. If you went into your medicine cabinet and it was all like big and puffy, that would tell us that we make O2, but that's not the case. It actually mainly stays on this side. And the reason is because there's no catalyst present to help that reaction get over that activation barrier. We see the reaction go forward when we apply peroxide to like wounds or whatever. Our blood is actually a catalyst that helps that reaction proceed forward. So here's the uncatalyzed reaction. This substance, when we think about it, right, that's a big hill to get over. And it's hard for that reaction to get over the hill, so the reaction stays mainly on the reactant side, and we don't see O2 produced. So what happens when we do introduce a catalyst? We introduce a new pathway for this reaction to go to products. And so in this example, uncatalyzed, this peroxide degradation is one step. That's what this graph is trying to say. But when you catalyze this reaction, you actually have a two-step mechanism. A two-step mechanism where the activation energies for either of those steps is much lower than the uncatalyzed version. So we see when we catalyze this reaction, it goes much faster. And that's what happens when we put peroxide on our skin or whatever, on our wounds. That's how we initiate our that reaction forward, by lowering the activation energy. And so you see, yeah, new pathway, lower activation energy. So tell me, the catalyzed reaction is the blue ones, okay? There's what we make intermediate and our product. So tell me, what is acting as a catalyst in the catalyzed reaction? Oh, and here's the two-step mechanism. What's acting as a catalyst? Bromine. Well, which one? Br2 or B minus? Which one's the catalyst? Br minus, yeah, so technically it's bromide. Bromide if it's an ion, yep. So bromide is a catalyst. How do we know? It is consumed in the first step and it's made in the second step. It's made, you get it back. Okay. So that's any other catalysts? Which one? H plus is also a catalyst, yep. Because it is consumed and then comes back at the end. All right, then anything else? What did I say? What's an intermediate? Bromine is an intermediate. So Br2 is made and then consumed in the next step, so that's an intermediate. Okay, so intermediates, the pink ones. My catalyst is the yellow one. All right? Okay. And so, so enzymes, I mentioned that enzymes also a catalyst. And here are the reasons. So in our bodies, we have these enzymes. There's a bunch of different models that biologists use to talk about enzymes. I'll be honest, I'm not much of a biologist. I futz my way through this, more of a chemist. But the idea here we can relate to our Arrhenius equation. Enzymes bring substrates, basically a fancy word for reactants, towards it. They help the reaction move forward, and then they release the products. So really an enzyme is also a catalyst. It operates by lowering the activation energy for the reaction to occur. So enzymes speed up reactions because they bring substrates, the reactants, close together, right? So if we think about the Arrhenius equation, if we bring the reactants close together, what factor in the Arrhenius equation does that improve? A, because A is what? Is the collision or frequency factor. So if you bring the reactants close together, you're improving the collision. So how an enzyme, a body enzyme works, brings the things together, you improve A. That's how you make the reaction go faster. Enzymes speed up reactions because of orientation. It puts the substrates in the right orientations to improve collision. So this also improves A. I would say, right? Includes, it improves collision frequency factor. All right, so enzymes will speed up a reaction because it also changes and weakens the bond energies, how strong bonds are in your substrate. So if you weaken bonds, pre-weaken bonds, how do you affect the Arrhenius equation, do you think? Activation energy, yeah, so what an enzyme does, that's how it speeds up a reaction. Pre-weakens the bonds, it actually lowers the activation energy. So you see all of these factors. If A increases, K increases. If EA, activation energy, decreases, K increases. So that's how an enzyme works. Okay, and so here's an example. Like enzyme brings together your substrates, all right? And so just due to the nature of the cavity of the enzyme, pre-weakens some bonds to facilitate reactions to move forward. All right. All right, so my favorite catalyst is your catalytic converter, all right, in your car. This is an example of heterogeneous catalysis. Oh, I guess I didn't mention this on the slide previous here. There's basically two types of catalysis. Homogeneous catalysis, that's where your catalyst that you add is in the same phase as your reactants. Those are the best kind of catalysts because you get really good collisions if they're all in the same phase, like if they're all gases or all aqueous. But typically what we see are heterogeneous catalysts, where you add something that's a different phase as your reactants. So if we look at the bromide acid catalysis, this catalysis is what kind of catalysis? Is it homo or hetero? Homo, yeah, homogeneous, because the catalyst, Br minus and H plus, they are both aqueous, just like all of the reactants as well. I mean, water is a liquid, but remember, aqueous means in water. Yeah, so they're all the same phase, so this is homogeneous catalysis. But in your car, your catalytic converter is heterogeneous catalysis, because your catalytic converter in your car is made out of platinum. Platinum is what phase? It's a solid, yeah. And so what your catalytic converter in your car does is convert some of the noxious fumes that come off of your exhaust pipe, so like NOx gas, SOx gas, uncombusted hydrocarbons, and convert it into things that are not so bad for the environment, like N2 and O2. I mean, that's already in our air all the time. That's what we want to convert. We can convert CO, carbon monoxide, that's bad, that'll suffocate you, into CO2, because it's less bad. That's stuff we just exhale. And your catalytic converter will also convert any uncombusted hydrocarbons to, again, CO2 and water. And so how your catalytic converter works is it uses rare earth metals like platinum, but they're a solid. Everything in these reactions are gases for the most part. So how we improve efficiency in a catalytic converter is we take that those rare earth metals, we put them on this honeycomb substrate. So you improve surface area to facilitate that catalytic behavior. The gases migrate to the surface, the high surface area surface of your catalytic converter, the honeycomb shape, to facilitate the reaction, and then the products go off. And so the honeycomb shape improves surface area. You can think of another way to improve surface area. If I just had a big chunk of platinum, think about that surface area. What if I ground it all up into a fine powder? Which one has more surface area? A big chunk or fine powder? Powder, yes, but can I put a powder in my exhaust pipe? What's the problem there? It would just blow away. Yeah, just blow away. And so kind of how we get around that, how we improve surface area for your catalytic converter is make it that honeycomb shape. All right. So also special about your cat in your car is that this conversion, the catalysis, is improved at higher temperatures. So oftentimes you'll see. So I mean, does anyone live in a inspection like county in Ohio? There's a couple counties in Ohio that require an emissions check. Does anyone live in one of those? They're usually near Cleveland. Okay, so anyway, I lived in Pennsylvania, right? And in Pennsylvania, they do require emissions checks. So what they're checking for is your exhaust pipe. And they're checking is, do you have the bad NOx gas, CO, uncombusted hydrocarbons? That's what they're testing for, because those are bad for the environment, all right? So I drove a real old car in high school. It was my favorite car. It was great. It was a 1988 Geo Prism. It was a hand-me-down from my brothers to me. It was great. But one year, like, it didn't pass the emissions check, right? It was really old. And so the guy, so I went to a shady, like, mechanic, as we all do. And he told me, he's like, you didn't pass your emissions check. But he told me, go drive to the county over, all right? So take the highway. He said, take the highway, drive to the county over, drive back. When you're 5 minutes away, give me a call, and I will check your emissions as soon as you come in. Because what that does is when you drive for like a very, very long time on the highway, you really heat up your engine, you heat up the gases that are coming out, you heat up your catalyst. And so when you heat up your catalyst, this conversion happens much more effectively. And so what my shady mechanic was just telling me was, heat up your cat, I'll test it again, and hopefully you pass. And so I did do that. I drove the county over, drove back, he tested it, I passed, but I did not pass the next year. We couldn't get it to happen, because what oftentimes happens with these catalysts in your car is they get spoiled by other substances like lead. If any lead gets through your system, it essentially kills that platinum that's in there. When you fill up gas, what do they call it? Unleaded. Yeah, because they used to put lead into gas as an anti-knock agent, but there's still avenues to get, your cat spoiled if you get any lead in there, right? Okay, so I like to talk about cars. So there we go. All right, so let's do one last example, and then we'll move on to chapter 15. All right, here's a 3-step mechanism. Will I ever give you the mechanism here? And okay, could you figure out the rate law for this mechanism? Why? No? Why? You don't know what the slow step is. Yeah, that's right. That's right. So I wouldn't give you this example unless I was really mean and said, here's the rate law. Which step is the slow step? If I gave you the rate law for the reaction and I asked which is the slow step, could you figure that out? Yeah, well, how would you have to do that? Test each and every one. So test if the first step was slow, the second step was slow, third step was slow. Okay, so, but that's a little harder. Probably won't ask that. All right, so here's a 3-step mechanism. What I want us to do here is just determine what is A, B, C, D, whatever. Okay, what is A in this mechanism? Well, actually, let's first get the overall reaction. It looks like C cancels. What else cancels? D, what else cancels? B, yeah, so this looks like it's 2A gives us X. That's it, right? Yeah? Okay. Okay, so what is A? Is it a catalyst? Is it intermediate? Nope, it's neither. Really, A is a reactant. Okay. What is B? It is a catalyst. Yeah, it cancels out of the equation, but what's special about B is that you add it as a reactant, it's consumed, and then it's produced by the end of the reaction. All right, C, what is C? Intermediate, cool. What is D? Also intermediate. And then what is X? Neither. Specifically, X is a product. Okay. Is that too bad? Nope. All right, so we're done with chapter 14. All right. All right, so that means chapter 14 homework is due on Sunday. But we have a holiday on Monday. So I'll extend it. Until when? I don't know. I'll extend it until, I don't know, Monday or Tuesday. I haven't decided. Because our exam is that week, so that kind of sucks. And what kind of sucks is that chapter 15 is assessed. Chapter 15 is assessed, but the homework for chapter 15 is probably not going to be due until after the midterm. So I really encourage you to, we're going to start 15 right now, do the homework, prepare for the exam, but the due date for the whole set won't be until after the midterm because I stay consistent with my policies. All right. Okay, so let's go to chapter 15. Okay, so we talked about in chapter 14 kinetics, small k, little k, baby k. That k is called what? Rate constant. Rate constant, small k, baby k. Rate constant lives inside your rate law. Rate equals little k times concentrations of stuff, right? That little k. Now, for the next month, we're going to talk about big K, right? So it's a different K, but it's bigger and it represents something else. So understand the difference between rate constant. That's what we talked about in chapter 14, right? How that is related to reaction rate, your rate law. Your rate law equals small k, rate constant times concentrations. And we're going to now talk about big K. Big K is related to small k, and I'll show you how. All right, so we're going to talk about chemical equilibria. All right, in Chem 1210, we looked at a lot of irreversible processes. Whenever we wrote a chemical, balanced chemical equation, we would just use a single-sided arrow. Just A becomes B, straight arrow. In 1210, we briefly talked about double-sided arrows, equilibrium arrows, when talking about weak acids and weak bases. All right, do you remember that? Strong acids, weak acids. The idea was if you memorize the strong acids, the 7 strong acids, then everything else is a weak acid. Weak acids are dictated by the equilibrium arrow, all right? And so back in 1210, we just said weak acids, this equilibrium arrow, both sides exist at the same time of your reaction. Now we're actually going to study it. Reversible equilibrium arrows, that's this double-sided or forward and reverse arrow, that's what we're going to study. All right? So if we look at this, the two differences, all right, irreversible versus reversible reactions. If I do and this is just an example, a combustion reaction, right? I blow up the balloon. I take your reactants and I turn it into products. Can I reverse the reaction easily once I blow up the balloon? No. Once you make the products, you can't go back. That's why we use just a single arrow, because it can only go in one direction. But what makes equilibrium different is that both the forward and the reverse reactions can occur, all right? And that's why we use this double-sided arrow. And so what you see, like in a solution of HF, is that you see the HF molecule present, you see H plus present, and you see F minus present all at the same time. Both sides exist. And that's what we mean by that double-sided arrow. If you look at this container, there's your HF, right, the neutral molecule, and then H plus and F minus, they are represented by those ions. So see how all of them exist at the same time. And that's what we're studying, equilibrium. All right? And so with equilibrium, and we mentioned this kind of at the tail end of mechanisms and rates, is with a equilibrium arrow, those fast steps, we said that the rate in the forward direction was equal to the rate in the reverse reaction. And so that's the big idea here that we're studying in this chapter with big K. Another analogy, with your forward rate equaling your reverse rate, if that is present, if your rates are equal in either direction, what you'll see overall is no change in concentrations of your species. And so an analogy is if you were taking an elevator that was or an escalator that was moving down, but you are walking up the escalator at the same rate, both at the same rate, if you were a passerby watching that person walk up an escalator, if the rates are equal, would you see that person move? No, they're not moving relative to where they are on the escalator. They're still walking. They still have this certain rate. We just don't see this macroscopic change in their position. And so it's the same thing with equilibrium. All right? Is there a question? No? Okay, all right. All right, so again, with chemical equilibria, the big idea, the difference is we are studying this double-sided equilibrium arrow and what that means. And so what you need to get through your head with this equilibrium arrow is when we have one of these, the reactants and the products are present at the same time. Okay, there is a reverse reaction and a forward reaction. They both happen, right? So how we express the magnitude of how much product or how much reactant we have in a system that's in equilibrium, we use what's called an equilibrium constant. That's what big K is. It tells us the ratio of products versus reactants that are present at equilibrium. All right, so when you go to bed tonight, also say to yourself, big K is generally equal to products over reactants. All right, so generally, K, products over reactants. So if I know the concentrations of products, I put that in the numerator. If I know the concentration of reactants, I put that in the denominator. So the magnitude, the value of K, tells us relative, okay, are more products present at equilibrium or are more reactants present at equilibrium? And again, we're going to be studying K for like a month. And that idea holds true throughout all of it. The magnitude of K tells us how much product versus reactant we have at equilibrium. So there's some different Ks that we're going to study here. Kp, where we study things that have pressures. What has pressure? Gases, yeah. So we put the partial pressures of gases inside these concentrations because pressure is analogous to concentration, right? So typically Kp is represented for gaseous samples. Kc, that C stands for concentration. So we can also have equilibrium in water in solution. So things that are aqueous typically have molarities, and then we put that into our K expression. But the thing is with Kc, gases can also have concentrations as well. So you should be putting anything that's aqueous or gas in a Kc expression, but only things that are gases go into a Kp expression. And we'll do some practice. All right, so what is K? Okay, so here is an example. All right, I have an equation, some chemical equation. H2 is combining with I2 and you get HI. It's an equilibrium because I have that equilibrium arrow. And I'm telling you both sides of the reaction exist at the same time at equilibrium. So here's a number of experiments where I adjunct to a vessel and then look at that vessel, what its contents is a little time later. So in this first experiment, initially I only put the reactants in the container, right? I only put H2 and I2. But then when I leave the vessel alone and I check back later, I see, oh, I actually have less H2 and I2 afterwards, and then I make some product, right? And so how we make our K expression is we take the products concentrations over the reactant concentrations, making sure that any stoichiometry becomes exponents. So what we see here is that our Kc expression for this equation, it's products over reactants, but stoichiometry becomes exponents. So Kc is equal to Hi concentration, your product, squared over H2 concentration times I2 concentration. They're both to the 1. So that's my Kc expression, right? And so once I check that vessel in experiment 1 over time, I look at those concentrations, I can plug in these values into the K expression, and I get this number, 51.5, at that instance, all right? So what's interesting is if I do the experiment again, but change the conditions, so this time in experiment 2, instead of starting with only reactants, I'll only start with products. So I'll just put products in there, all right? And what we see over time, it doesn't stay that way. It wants to approach equilibrium. What happens is some of the product is consumed and you make some reactant, right? But the cool thing here is if you take the ratio of products over reactants again, you get 51.5 again, right? You can change it even more, like halve the amount of product you have, right? Still the same thing happens. The reaction goes in reverse. You consume some product, make some reactant, but if you take the ratio, you get 51.5 again. even with different concentrations. And then in this example, we, just put some random amounts there. At equilibrium, your concentrations will always, multiply or divide to the number of 51.5 if that is your equilibrium constant. So that constant, again, tells you the ratio of products over reactants when your system achieves equilibrium. That'll always go towards that, that point to reach equilibrium, and we'll talk about more why when we talk about chemical thermodynamics. All right, and so that's the big idea, that your reaction will approach equilibrium. It'll react until it does approach equilibrium. All right, and so here is just kind of a summary of how we get those K expressions. This one is Kc because things are concentrations. So Kc, C stands for concentration. So you want to put the molarity of anything that has a concentration into that K expression. Does substance C have a concentration? No? Yes, it does, because it's aqueous. Does D have a concentration? Yes, because it's aqueous. Does E have a concentration? No, because it's a solid. Great. What about A and B? Do those have concentrations? Yes, they do, because they're aqueous. So what we see in our K expression is we only have C and D and A and B. E does not show up, okay? Because though E does not have a concentration, it's a solid. And so again, stoichiometry becomes the exponents in your K expression. So do not forget that. So we need balanced chemical equations. All right. And so you see here, here's Kp. P means pressure, so you want to focus on gases. So C and D are gases, they have pressures. Put those partial pressures in your Kp expression. But does substance E have a pressure? Nope, it's a solid, so it gets left out. And then A and B are also gases, so those go into your Kp expression as well. Right, so just remember, Kp, gases, things that have pressures. Kc, concentration, things that have concentration, which can be anything that's aqueous or anything that's a gas, if it's a heterogeneous mixture. Okay. All right, so I want to talk about the significance of big K and how it relates to kinetics, because it does. All right, so we said in chapter 14 when talking about fast steps, all right, equilibrium is where the forward rate of your reaction equals the reverse rate of your reaction. So I'm talking rate laws, like rate equals K times concentrations of stuff. So for this reaction, it reaches equilibrium when the net amount of particles going to the product side is equal to the particles going in the reverse direction, to the reactant side. Right? That is what equilibrium is. I like to think of it as like you let a bunch of kids loose on this playground, okay? You let them go for a while, and at a certain point, the kid's going on one side versus the other side. Like every kid that goes over, another kid will go to the other side. And then so you don't see this net change in stuff on either side. You just see this, those two rates kind of cancel each other out, so to speak. So you don't see an overall change in concentration on either side. All right, so forward rate, reverse rate. Each of those rates have a rate law, right? We talked about this in chapter 14. So if we assume that this reaction is an elementary reaction, so we have A plus B giving us C to D, do you agree with me that the forward reaction is A plus B gives us C to D? And then the reverse reaction is C plus D gives us A to B. That's the reverse reaction. Okay, if they're elementary steps, we can get the rate laws for both, right? So the rate law for the forward reaction is rate equals K, rate constant, times A times B. But is the rate law for the reverse reaction the same? No, it's not. Because in the reverse reaction, the products are now the reactants. So in the reverse reaction, see how C and D are now in the rate law? Okay, great. So this how equilibrium works is we say, again, that the forward rate is equal to the reverse rate. So what I'm going to do is just set those two rate laws equal to one another, just like we did in chapter 14. right? So when we achieve equilibrium, we're saying, okay, the forward rate is equal to the reverse rate. The forward rate law equal to the reverse rate law. So putting that all together, I get this. So there's the forward rate, there's the reverse rate. See how I set them equal to one another? So what I'm going to do is move some species around so the concentration terms are on one side and then the rate constants are on the other side. So when I do that, how do I do this? I'm going to divide both sides by A times B. And then I'm also going to divide both sides by K, rate constant in the reverse direction. And so we get this expression where the ratio of the forward and the reverse rate constants equals products over reactants, right? And so that ratio is equal to our equilibrium constant. So that's how we get, that's numerically how we get our equilibrium constant. You know, I just told you it's products over reactants, but this is why it's products over reactants, because we're utilizing the rate laws of this elementary reaction where we say forward rate equals reverse rate, right? So that's where it comes from. Like you, on an everyday basis, you're gonna always think rate constant, equilibrium constant, big K, is equal to products over reactants, but this is why, because we rearrange the rate laws, and that's how we get it. All right, so, cool. All right, so we see that rate constant equals the ratio of the, equilibrium constant equals the ratio of the rate constants. See how there's a lot of K's and like constants coming around, so do try to keep them straight, unlike me. Your equilibrium constant is equal to the ratio of your rate constant, which is also equal to the ratio of your products over reactants. Okay, so let's put that all together into this diagram. Okay, we're going to try to figure out, is K, equilibrium constant, a big number or a small number? All right, tell me. In which direction is there a small activation energy, in the forward or reverse? Reverse. Okay, cool, perfect. So what does that tell you about the rate constants? The reverse should be faster, right? Or the rate constant for the reverse reaction is larger. What equation tells us that? The Arrhenius equation. K equals A times E negative EA over RT. Rate constant increases if activation energy is small or if temperature is large. But in this case, we're just changing activation energy, right? So we're saying that in the reverse direction, activation energy is small, so the rate constant in the reverse direction is big. Do you agree? Yes. All right. So if that's the case, if the reverse rate constant is big, how can we deduce the magnitude of K? K, our equilibrium constant. Is equilibrium constant a big number or a small number? Small number, yes. It is that right? Yeah, small number, all right? So if our equilibrium constant is a small number, and we basically say, okay, K is the ratio of products over reactants, is there going to be more products at equilibrium or reactants at equilibrium? Think about it. You said K is small. How do you get a small number? Do you put a big number in the top or the bottom? The bottom, yes. If you put a big number on the numerator or denominator, you get a small number. So, do we have more products or reactants at equilibrium? Reactants, yes. That's how we were able to get all that information from just this graph. Here's another way to think about it. 100 kids on a playground, and you let them loose, right? And you let them go for like half an hour, and you come back. Where are most of those kids going to be? At the bottom of the hill or the top of the hill? They're just crazy running around. They're probably all going to kind of accumulate on the bottom of the hill because it's like this low energy spot. I guess that's how I like to think about it too. So in that, if you think about it that way, we say that there's a lot of reactants present at equilibrium, but we deduce that from the rate constants, the activation energy, and the meaning, the significance of what equilibrium constant is. Okay, but for the most part, you won't really be thinking about equilibrium constant in terms of rate constants. You're mostly going to be thinking about it in terms of ratio of products over reactants. That's 90% of what we're going to do here. All right, so let's do some. Okay, let's consider the Haber-Bosch process. All right, so the Haber-Bosch process, Nobel Prize worthy. It's what almost cured like world hunger. It solved world hunger. So let's get the equilibrium constant first, and I'll talk about this evil guy later. All right, Haber-Bosch process. Is this an equilibrium? Yes, why? The double arrow, yeah, that's not a mistake. I put that in there deliberately. So you know to use big K. All right, so let's write the Kc expression for this. Oh, but everything's a gas, so is there nothing in there? No, gases have concentrations, all right, and that's okay. If I know how many moles in the container I have, and the volume of the container, N over V, that's molarity. So Kc for this expression is just products over reactants. So NH3 squared, right? Because there's a 2 stoichiometry over N2 concentration times H2 concentration cubed. That's Kc. Right, that's the expression. You can look up what the value of K is at a certain temperature if you wanted to. Right? There's always values associated with that ratio. Okay, so what's special about this reaction? If we think about where all the nitrogen is in our world, it's actually mostly tied up as N2 gas. In our atmosphere, N2 gas is very, very stable because if you remember Lewis structures and stuff, N2 has this triple bond. It's very, very, very strong, so it's hard to break. The problem is that plants, okay, in order to grow, they need a lot of nitrogen, and so getting the nitrogen from the air is very difficult. That's why we use fertilizer on plants, to give plants nitrogen that they need to build those amino acids and all that stuff, plant stuff, all right? The problem is there's a certain point of time right around World War I and II that, you know, they actually hadn't invented fertilizer. Fertilizer wasn't something you could just buy at the store like we can now, like you just buy Miracle-Gro. Back then it didn't happen. What they did instead is they put compost on plants, like, you know, like excrement and stuff, because that was their highest source of nitrogen. Nitrogen that was bioavailable to plants, because when it's N2 as a gas triple bond, it's not bioavailable because it's a very strong bond. So Fritz Haber or Haber, I don't know, it's German, solved that problem through this equilibrium process, right? So it was a really, really big leap forward in chemistry and technology. He learned, studied that this process, turning hydrogen gas, nitrogen gas, and making ammonia so it's bioavailable to plants, was a giant leap forward for chemistry and for society, because now we could make fertilizer instead of composting stuff, because that's very time consuming, right? So he figured that out. Okay, he designed a machine to utilize this equilibrium process, and so that was great because he was able to help the world produce a lot more food. And so I think the statistic is that 50% of the nitrogen in your body was produced by this Haber-Bosch process today, right? So that's how we were able. That's how the world is able to accommodate. How many people live on the Earth? 2 something billion. 8 billion, jeez. Okay, I don't know. All right, 8 billion people live on the Earth, and it's due to Fritz Haber. All right, but see, we can't always talk about like all the good stuff that chemists do, right? Because Fritz Haber wasn't the greatest guy. So he did this. He won his Nobel Prize, but he also was German, and so after this discovery, he kind of used his resources and started exploring chemical warfare, right? So he invented chlorine-based gases that would asphyxiate soldiers. So on one hand, he solved the world hunger and food crisis, but he also invented like war gases that killed a lot of soldiers. And so, I mean, this is not an ethics class, okay? But I just want you to think about that, you know, that he did good, but also bad stuff. And so, yeah, just think about it. His family was very against what he was doing. They were all like pacifists. Both his wife and his daughter killed themselves because I think they were ashamed of what he did. Very interesting life. There's a lot of podcasts about him. So you think about that, okay? Not an ethics course. I think if, you know, so the question is like, was he a good guy or a bad guy? I don't know. What do you think? He solved world hunger, but killed a lot of people, or was the reason he killed a lot of people. So yeah, it's a thing to think about. I don't know. If you want to talk about it, we can talk about it. So you can think about that, all right? So let's do a calculation. And then, yeah, so there we go. There's a guy. He even looks like that evil guy from Austin Powers. Yeah. Okay, so not all chemists are good, is what I'm saying. Okay, so let's actually do a numerical problem. Okay, so here is our equilibrium, and here I'm telling you the concentrations at equilibrium. This is just testing. Can you plug in the numbers with the right expression? So Kc is always equal to products over reactants. Be sure to include those correct superscripts. So Kc equals NH3 concentration squared over N2 concentration times H2 concentration, and that is cubed. So just plug in the right numbers, and we should be able to calculate what our equilibrium constant is. And I'm telling you, this is at equilibrium, so we can just plug it into the K expression. So we have 1.4 molarity on the numerator, and that's squared. N2 is 0.3 molarity, and then H2 is 0.9 molarity, but that all is cubed. And so you get some number, I think it's like 9. What's special about K is that it's unitless. It's unitless, so we don't care about the unit. So you might actually calculate it and see, oh, it's molarity squared on the top, molarity to the fourth on the bottom, but because it's just a ratio of products over reactants, we just say that it's unitless. And so you should always understand that the species inside the equation are molarities. Great, so it's 9. And so these are the concentrations you would measure at a certain temperature. We have the equilibrium constant now. So with that information, we can determine what the concentration of a species at equilibrium if we are given other information. So here in the follow-up question is, what is the ammonia concentration at this same temperature if these are the concentrations of the other things? So the term here is at the same temperature. So this tells me that I know what K is. K is the number we just got. So it's 9 point whatever, 9.0. And so we're just gonna plug in those same numbers, or use the same equation, but just plug in different numbers and solve for something else. So in this case, what am I solving for? The numerator, NH3, all right? So putting this all together, K is equal to 9 equals ammonia concentration squared, that's what I'm solving for, over nitrogen concentration, 0.6, times hydrogen, so 1.8 cubed. And so solve for NH3, take the square root of those numbers, and you should be able to get what is the concentration of ammonia present in order to achieve that equilibrium constant, right? So just a little bit of reading comprehension, plug in the numbers in the correct spot. So you solve for that value and you get, whoops, I erased it. You plug in that value and you should get that ammonia present in order to achieve that equilibrium constant is something like 5.6 molarity. Great, so there's a good place to stop. We'll pick up and talk about the difference between K and P. We're gonna be doing a lot of math on Friday. We're going to be doing a lot of math, so do bring your calculator. I'll introduce ICE tables. Yes, ICE tables are fun. If you like BCA tables, ICE tables are similar.